So, dzień dobry, witam wszystkich. Welcome everybody to my talk. I will be talking how you improve the signal, reduce the noise. This is my Twitter handle and the internet, and what I've noticed yesterday, it's my company's logo could be flipped 90 degrees back to form the Lambda, no, but I will suggest this after this talk. So, during the day, I'm a software developer in finance. I don't use architect very much because it's a pejorative name in France. And during the night, working my startup project, rocketcv.pl, but this is just the draft online, and it's not the final application that we want to deliver. And the rest of the time, I'm running two user communities in Paris, F# user group and domain-driven design user group. I've been first involved in the domain-driven design user group, and when I discovered functional paradigm, I found that it fits very well with domain-driven design user group. And also the rest of the time I'm trying to blog, tweet, and play guitar, but there is no much time left. So this is very occasionally. So this talk is about the benefits of moving from object-oriented programming to functional programming for a startup project. So today, many startups, when they want to write their application, they choose rather dynamic languages like Ruby, because maybe there is less constraints and they think there's easier and faster to build a startup project. But what I found out that using F# for a startup project is a very powerful thing to do, and you can deliver very fast. I've always been an OOP developer. It's been maybe 15 years since the very first beta of .NET. I started to develop in C#. But this is what we can say. I've changed my mind, and this is the really niche citation. The snake which cannot cast its skin has to die, as well as the minds which are prevented from changing their opinions, they cease to be mine. So this is the motto for this talk. And building a startup is not just about writing the code. There is many tasks that are spent on non-technical things like business plan, market surveys, advertising, legal stuff, like privacy policy, terms of use. This is very important. You can just go into the wild and be happy to collect all the information from user. So after some organism like diodu, I think it's in Poland, they will catch up, they will catch you, and you have to be responsible for what are you doing online. There are some other technical tasks that are not involved directly with coding, like you have to choose your hosting platform, define your build and deploy processes, and integrate with external API services. Great. So we've integrated with several APIs like Stack Overflow, GitHub, and so on and so forth. So there is, much time you have to spend studying all these APIs. And the time spent for coding must deliver a real business value. But can we measure the part of business value inside our code? This is very hard, and I don't know an automatic tool or metric that can be used to do that. The attempts were made. It's Simon Cousins compared the same application written in C# and in F#. The blue one is C#, and the green one is F#. It's the same application, and this is the lines of code. So this is the braces, null blanks, null checks, comment useful code. So there's a very big difference. And there's some statistics from his website. You can find it here. So for example, null checks, 3,000 null checks for C# and only 15 for F#. And I think 15 is because they integrate with some C# code, so they have to check for nulls. So we can, for example, Yes?
One quick question, can you go back?
Yes?
What about comments? So do we assume here that in actual code we just don't comment because it's a...
For me, comment, it's a noise. You have to name your classes, your methods in C# to not use comments. If you put a comment, it has to be gold, like Kevin Henley said. It has to has a value. You don't just. In fact, you shouldn't use comments just for. No, instead of using a comment, just write a code that don't need comment.
I think the difference is because they're proportional, like the amount of lines of code, and that's why there's so much less comments, because there's so much less code to comment.
Yes, and also because you can express maybe in more concise way in F# than in C# your ideas. So in electronics, they use a signal-to-noise ratio. It's a measure that allows, for example, if you buy an amplifier or a DVD player, to know how good is a signal compared to the background noise. This is the simplest formula. So this is a mean of all the signals divided by the standard deviation, which is the of all background noises, and the result, the bigger the result is, the better it is. So can we adapt this to the code? I think it's possible, but we have to define what the signal is in our code. And signal, it's an information that produces a business value, and everything else impeding the transfer of this information is just a noise. So we will discover the different kind of noises we can find in our code. And what's important also is that information conveys knowledge, and the knowledge is derived from facts. And fact, it's produced by business use case, and this is the business value that we look into our code. So some of the signal properties. Fact that happened is incorporated in a time and should be immutable value. Let me give you an example. For example, if you have a friend and he comes to you and says, I've moved from this address to the other address. Do you automatically clear the old address in your head and put a new address in your head? No, I don't think so. You know that he has now a new address. You will remember this new information as new address, and you will keep for some time the old address. You will make usage of it or not. These are the facts that can be discarded, but they are no mutated. In object-oriented programming, we mutate. We take the old fact, we mutate it with the new value, and we save it. And this is a very important distinction because all the decisions are made on facts, on our past experience. So if you build an information system, you have to have all these facts that happened before to compare them and to make decision based on them. And noise infers with the signal and don't contribute to knowledge. And everything which infers signal, yeah, that is the same. So for example, relevant or false data, fact mutation, and everything that hinders readability of facts, even your language structure and code. And there is several categories of code noises that I've identified. There's organizational one. For example, if you have many assemblies, it's hard to reason about the dependencies between those assemblies. So we have to use a static analysis tool to discover this. Readability, how it is easy to read your code, because most of the time, 80% of the time we are reading the code, and 20%, or maybe even less, we are writing the code. So it's very important that the code should be readable to move faster in development. And correctness, it's For example, your type system in your language allows you to write a robust code, or you have to do null checks everywhere, and try-catch exception everywhere, and correctness, expressiveness, it's how much plumbing code do you need to glue all the use cases together, and also frameworks for if you use dependency injection, and mocking frameworks for testability or ORMs and the stuff like that. And the effort is just a subjective, and complexity you can measure it with your static analysis tool. So to be simple, we can make a theoretical metric. We are interested of the percentage of the line of code for domain use case divided by the total lines of code times 100. This will be the percentage that we are interested in. So, as I said, there is no automatic tool to measure it. When I've written several business cases in my startup project, I started to count all the lines. Because, for example, if you take a static analysis tool, it doesn't include, for example, braces and in C# and all the stuff like that. Or, for example, when you have a typed variables, the type declaration doesn't count also like a line of code. So this can be measured, and the categories are just a subjective estimation, effort, reliability, organization. And let's try to look at 3 different implementations of the same use case. And the use case is very simple. Let's create a REST service, which is a registration process business. Rules are very simple. All fields for the registration are required. Password, email, privacy selection. Password should match the password policy. Email address should be unique. And if user is from trusted provider, then email is automatically confirmed. For example, if you come from auth, like Google or Facebook, you won't confirm the email once again for the user. You can trust. And if not, you have to send an activation code to the user. And after this is saved. So I used ASP Web API 2, and we'll have 3 implementations: C# native implementation, OOP, and F# at the end. If you were to draw this business use case, it's very simple. You have just an input, validation, business rules, business logic, and at the end there is a fact. We then save this fact, or send a notification, or return it back to the output. There is some error cases that you want to break every time you run into an error. So this is my REST service action for registration. That there is one parameter, which is the resource representation of registration. We post that resource. So after we check if this is valid, we check if password match the policy. This is very simple. If not, we say send a batch request. If not, we'll go on. We open a database connection. We check if there is already account that exists. We encrypt the password. We produce a domain account. And then there is a state mutation. We don't know. We have to go to confirm email method to be sure. But we suppose there is some state mutation. And at the end, page 3, if there is email confirmed, so account can have an email that is confirmed or not, we make the decision based on Boolean flag. We will send an activation code, or we just return OK response. So this is very easy. This is how it looked like, Mayday feedback. So there is an input, the information goes through. This is the green line through the decision cases. Decision is made in the blue boxes, and the fact is produced at the end, which is the account, domain account, which is mutated 3 times before it's saved to the database and returned to the to the user. Some observation, this is a procedural code. There is a state mutation every time. So we can say that my account at the time t was like that or like that because we've lost track of every changes in my business. So this is very hard to read what happens in my code. And decisions are made by intermediate states to steps, everything orchestrated by a client, and you cannot test it very easily. You have to do an integration test of the whole, but not different steps one by one. And this is some statistic from this very simple use case. We have something like 400 of code, and there is only set percent of useful code of business use case. The rest is not very important. Correctness, there are some null checks, the try-catch, exception braces, there is a use of frameworks, there's ORM frameworks, and dependency injection frameworks. So this code, for me, it's not very important for the use case. It's just there to support your use case. But we can do better in object-oriented programming. We have to use abstractions, and the code should not be procedural. Can we do better in refactoring with some abstractions? So we can find out this abstraction. In general, what people do is we need to test. So we need abstractions around some of the features. So for example, e-representation validator, i-registration service, i-notifier, i-account repository for saving to the database. This is very standard. The refactored OOP implementation, it's quite similar, but not, now instead of using just code, we will use implementation of abstractions, of interfaces. For example, validator validate this response, and after we can use registration service implementation to check if user can register or not. And registration service is also responsible for giving back a domain account. But what if this is null? You have to check all the time if this is null, because if someone will change the implementation of register method, they may say null or whatever. So we have to protect yourself from that. And after, there is a standard check if we should confirm subscription, and if we should confirm, we will send an activation code and save to the database. So now, this is quite different from what we saw before. What's important that we've introduced some abstractions, and now this is the relationship between the abstractions. So the composition of our application is based on abstraction that we disposed and the relationship between them. So this is not very easy to follow. When you follow the green lines, you have to have in mind all the relationship and to understand your code. And what happens in your mind when you read your code, you try to follow all these lines to make a mental model that will be easy to read for you and to understand. So now we've used abstractions for composition. There is also a state mutation, and but now this is testable. And if we look at some statistic, we have twice code than before for the simple case, and the useful code for my domain use case, it's only on 5%, which is lower than with the simple code that we had before. And it's normal because we have much more line codes for the abstractions for the framework that supports dependency injection and so on. No, so for example, this is a C# class constructor. For me, this is a noise. This is not a direct support for your business use case. It's just here to glue all the abstractions together. So this is a language construction, so we can do differently, but people generally do this construction injection thing. So when you introduce some ORM frameworks, DE frameworks, and mappers between different layers, all this stuff is noise. And when you look at the simple solution explorer in Visual Studio, you will see all these classes in interfaces that are very, very big just to support a simple use case. And what's important that we've introduced one abstraction per implementation just for testing purpose. And this violates a reused abstraction principle, which says that we should have several implementation before introducing an abstraction. And what is interesting that in object-oriented programming, abstraction can be set up front. The abstraction should be discovered after some use cases that you find that there is a need for an abstraction. So if, for example, you have 3 different implementation, you can go for the abstraction. So I think the abstraction that we've introduced are not good anyway, but it means that it's very hard to find a very good abstraction in object-oriented programming. Can we do better with F#? But we try to improve a signal with F#, and HTTP, it's just a function, HTTP, request response. It's very simple. So we can define also a business use case as a function. We have an input and a fact that is produced at the end. So if we use it with HTTP, it can be like that. Request, then we invoke our business function use case, and then we produce a response. But what if, for example, there is a happy path, but if we wanted to handle all the errors along the way? There is a support for that in F#. We can use types that are called discriminated unions. And this is taken from railway programming, so from Scott Vlashin. So we can handle a success and a failure, and you can pass the result along the way in your business use case, and each time you have to handle both cases. So there is no, you have to handle them both, and you can just say, I would like to handle just success or failure. All the time you have to handle both. And you can also model error, like categories of the choices of different errors, validation, account exists, a database error. This is very readable, and you can see what can happen in my application. So if I rewrite the function, I can say that this is HTTP request, we have an input, at every time we are a result, which might be a success or error, and we produce a response. So let's try. Business use case, validate input, invoke domain, persist, and return result of error. So step 1, input validation. We have a password policy function that takes as input a registration representation of the resource, and then we match on the regex pattern to say whatever this is a success, we return a success, or if it's a validation error, we produce a validation error. So matching pattern in F#, you have to match all the use cases. If you don't match, you will get a warn by a compiler that will tell you that you didn't match all the cases. So this is less error prone. And at the end, you have a signature of the function, which will take an input and produce a result of registration or error. Active patterns enable you to define named partition that subdivide input data. So we can use these names in a pattern matching. So we define here match label, and we can use it in the matching pattern, like discriminated union type. But this is on a string, so the code can be very generic if you want. And then you can compose all the validation together, and you have a validate all, and inside of that function you can compose all the functions. So this is the signature of the function. It's the same as before. You can define your operators for composing a function. So this is an operator that will, depending on the successes and failures, will concatenate errors. So we can have them all at the end, and will also invoke successes to pass to the next function. So this is all the time we have the same function signature. This is a generic because we don't have at the point where if it's a registration input or something else. So this is a generic code. And after the use case, we can define like that. For now, we have just only validation. So we validate all, and all the time the same function signature. So notice that we don't provide any input for the function. We should have a registration representation input, but we don't provide. So the output is the function that waits for the register representation input, and this is what's called partial application in F#. So if you don't provide all the parameters to the function, it will produce intermediate function that will wait for the parameters that you can provide at the later time. So this is a very powerful design tool. And we'll see after how it composes all together. And the next step is to design with domain types. It's very important to express what your domain is capable of. Before, in OOP implementation, we had this flag is confirmed email. And now we can state that email on line 5 can be unverified or verified. This is very important because when you make decision, you have all the time to handle these two cases. What we do if the email is unverified, what we do if the email is verified. And if you take an address email in the other function on like a parameter, you have to match all these cases. So there is less chance that you will make an error. And if you add some more choices to this type, compiler will warn you that you have to handle these new cases that you add. And this is data-oriented, but it's normal and fine for data to be exposed and not encapsulated, because the data is immutable, so we can have a function that's misbehaving that will mutate this data. And it's like in parallel set, it's better to have 100 functions that operate on one data structure than 10 functions on 10 data structures. And the next function, we just map the register representation to our domain. So we will produce a fact, which is with email address unverified, because we didn't do any verification yet. And we return back to our use case. Then we can compose with the validation. So, you know, this is like a chain. Validation, validate all, and after validation, normalize email. And we have similar signature at the end. This is just the same function. We have a map function, but because some types, for example, one function can return a register implementation and another one an account, which is a domain object, so we can map on the input and to apply the new function to the success or return a failure. Just the function that serves for composing that you will know at what point and one point in time. So if we try to confirm email, you see that I have to handle all the cases, unverified and verified. And if account provider is off, I can say that I will produce any fact. I won't mutate a fact that was produced before, but this is a new with verified email. So the fact before I can discard or I can use, for example, for later use. But this is very important. And if not, I just return the account like it was before. And in the case it's verified, it's not more because we were producing unverified email before, so it can be verified at that point. And then we return to our use case. It's, very simple to read what happens in our application. We have all this registration service, try confirm email, and set activation code. And bind function just allows us to apply the result to the function when it's success, and when it's a failure, we return a failure. So this is all the time we handle two types. And at the end, we can persist. This is a persist registration. And the particularity of this function is that when you persist, there is no output. So we can apply just a function t, which is here, before saving to just return the output. So we can keep our function signature at the end. And try catch also, very easy to produce a success or a failure if there is an exception. And there is the only one try catch exception in a case when you are talking to database. And after there's just persistence mapping with type providers. And type providers is an adapter component that reads schematized data service and transform them in types in the target programming language. So, for example, there is the type provider for database. So we have a strongly typed new record with all the properties with IntelliSense, but there is some other type providers for CSV, for JSON. So it's very simple to work with them. And the final business use case composition is just a function of all the steps. We have the validation, registration, that database, notification. We can go even further. We can get rid of map and bind function. We can define our own operators. So this is one of the operators that we can define. Operator is just, composing one function to another and applying a bind function. So the code is even more readable. Similarly for the map function, we can do the same. A map function is also an operator map. We apply one function, compose with another, and return the result. And the last piece of application, we have our registration controller of web API, and we pass to the constructor just our business use case, which is here, use cases registration start. And in the action, we just match on the use case, which is a start process. It's called start process. We pass a representation that comes to our action handler, and we match on the success and on the failure. And depending on what the failure is, if it's validation error, we can return a badge request. If it's a account exists, we can return a conflict. If it's a database error, we can return internal server error to the user. And in the success case, we can return a created option with activation code. So the decision is made at the end of the business use case function. It's very simple. You have this all stuff in one place, and it's very readable. We can do even better. because when you see there is some matches that are included one into another, this is not very, beautiful. So we can introduce a maybe res, which is a computation expression that will handle of this state passing behind the sense. Computation expression, you can then define very simple like that. This is what I've made for this. We will just bind the function if there is a value. If there is no value, we will return none. If there is a value, we return some, which is like a nullable in C# to say there is a value or there is not a value. If there is a value, we will return a sum of the value. If there is no value, we will return none. And we have to handle sum and none all the time in all the cases, like a regular discriminated union. And the testing is very easy at the end. So this is the case for post returns OK on a valid data and trusted provider. So this is my start business use case. I can this is a function, so I can say whatever the input, return this result. Then I pass it to the controller. When I invoke my action, when I post to that action, I will check on the result of the test. And if I rewrite all these use cases, you can see that it's very similar to the theoretical use case that we have drawn at the very beginning. So we have an input, validation, registration. Everything is composed very easily. And then we return a result, and we match on success and failure. Some observations. There is a composition for functions. Functions are also values because we can pass functions to other functions. No state limitation, and there is a big business use case function, very easy to spot and if you want another business use case function for testing, you can easily replace it with whatever you want. And what's interesting that the lines of code, it's like a simple implementation in C#, but this is fully testable, there's readable, and the code for business use cases as 23%, which is big percentage. And for example, frameworks took 28% because the code that is involved with web API took much place here. But if we were to use another framework, maybe the result would be different. And if you compare two solutions together, this is the same testable use case in F#, and the other one in C#. This is very easy to read, and in F#, there is no folders because when you are new command to F#, you start with the bottom layer, and the bottom layer is the entry to your application, and you go up through different layers. So we've improved the signal because there is no need for frameworks for dependency injection. We use partial application, no need for AOP frameworks. You can use higher level functions for composing the other functions together. You can use computation expression also for this. No need for ORM frameworks. With simple type providers, you can do most of the things that you need to do, and you don't need to know 23 object-oriented programming design patterns, and even knowing just the map and bind function, you can compose very easily in F# to produce an application which is very nice to read and testable. And I heard this, Rich Hickey said, OOP promise reviews. It's a big lie, in fact, because it's very hard to find the proper abstractions and to compose them together. So that's why we have so many one-to-one between implementation in interface. So the values shared clearly, nobody can mess up, and so for example, let's create a REST service can turn very bad if you use a bad tool, or if not is carefully used, but everything in a life can end very badly after all. For example, let's saw this board. This can, or let's install this air conditioner. This is very easy. Or maybe let's get this party started with the electrical plug in the middle, and then the end, let's get some double shot. Be careful of what you are using, and F# is the language that helps you to avoid all these problems. And Murphy's law, anything that can go wrong will go wrong. So some references: F# org, F#, hashtag, the F# for fun and profit. And at the end, there is a conference in Paris in May, and we'll have a full track with people from F# works. So, thank you.
Thank you very much. Any questions?
So this is the second time in, I think, 2 weeks where I see the railway programming from the F# for fun and profit used. Do you know if it's available somewhere, in NuGet or a library, or we will keep, copy and paste from the page for every of our projects?
F# railway programming is very simple idea. So there's, I don't know, maybe 10 functions.
Like guys, just yesterday created a GitHub project on FS projects, which contains all these helper functions from railway programming. Like Stefan Fortman and Scott created that project, and it's like brand new yesterday.
Yeah.
But it's one file and it has 108 lines.
Yes, I used for my project only 2 functions, bind and map, and I used also a type, which is the very simple type, because Scott has a much complicated type.
The project is the enterprise-ready version, so it's 108.
Yeah, and for example, this is actually the business use case that I made in that way. They're actually in my project and on Azure, and there is no problem with that.
I have a question, because you were talking about development time because of a startup, like the value. So how long did it take you to build this version versus the native, the naive, or the object-oriented version?
Easily, I can say 70% less time to work with F#. Because it's you have your starting point, which is the function, and then I compose all the function along the way, and I don't care about all the frameworks, everything. If I need a function, I plug into the business use case, and in fact, what I want to do is just to take input and then to save it to the database. And when I first came to F#, I started to do some, research on different APIs, and it worked very easily. And I was surprised of how I was started just using F# and it worked right away. So that's why after I moved everything to F#.
But the version, like, this is a simple REST API, right? So doesn't the .NET whole stack basically auto-generate all this code for you, like, just for free?
No, you have to handle it. You just have the controllers and the action, which is provided by the framework. But after, you have to code everything you want to do with your API. There is no automatic code I'm not aware of. Or maybe if you are using some scaffolding with entity frameworks and stuff like that, but this is very brittle code, and I don't find it very testable. And Well,